In this installment, we're going to take a look at the AP formula sheet and make some connections to many of the formulas that we have learned so far this year, as well as to focus in on the formulas from this particular unit. So looking at the formulas, starting up at the very top, we have this first grouping of formulas, which I'll color in blue. And these are the kinematics formulas. That's their topic, so they are kinematics. And the versions of these formulas that I have used and taught you are V equals AT plus V0, X equals 1/2 AT squared plus V0T plus X0. And the third one, V squared equals V0 squared plus 2A delta X, which is one that you don't really need to use. These next two equations, or the next several equations here, this one and this one and this one, we will just say they're not here yet, but they are forces gravitation and circular motion. And this formula here, the very first one, we recognize as Newton's second law, which is F net equals ma, and F net is the sum of the forces, just rearranged. And then in our next section, we have this and this, which are our momentum formulas. So momentum is what it is, and we have J equals F bar delta T equals delta P equals M delta V, and that would cover those formulas there for us. And then we get into work, energy, and power. And so kinetic energy equals 1/2 mv squared, or the change in kinetic energy is 1/2 m delta v squared. And that's important because that's the work energy theorem. We have the change in energy is work, and the force parallel times the distance, and FD cosine theta. I will put out the conservation of energy, which is this, an additional formula that is not present, and we would say that the initial energy, the energy of the system, is going to be equal to the total mechanical energy plus the other energy plus the work. And then in our third formula here, we have power is work divided by time, is force times distance over time, is force times velocity. So some missing things there. There's a large next section which will look fairly familiar. They'll look similar to other equations because they are. This is rotational kinematics and dynamics. So we learned linear kinematics, linear momentum, linear forces and energy. Well, in this second part of the course we're going to be moving into, we'll be applying all those concepts in a rotational or circular setting. Then down below this, we have our behavior of springs. So we have F equals Kx, and Hooke's law basically says that the applied force is directly proportional to the elongation, or that the ratio of those two is a constant, the spring constant. And then we have the potential energy of a spring is 1/2 kx squared, similar version. This formula is sort of an odd man out. It's density. Greek letter rho is mass divided by volume. Then over here, we have energy, another work energy power formula, where EPG is mg delta Z. These fellows here are simple harmonic motion in waves, which we don't need to know yet. And this last bunch is gravity. And you've seen this one. The force of gravity is mass times the acceleration caused by gravity, or the gravitational field strength. That's one you've already seen. And so those are our formulas in AP Physics 1 and the translations of them that I have taught you so far.